What's up? Y'all doing good? Y'all ready? Sure. Is that what you wanted me to do? Since you asked first, I'll let you. Thank you. $24. Oh yeah. Didn't I do 24? Hold on. I don't think I did 24. Let me see. You know, it wouldn't have been day 4. Would have been day 4. Maybe not. It's funny. Can you all see on the side? Anyone who uses OneNote, when you write in here, it tries to automatically name the page based on what you wrote. It named this one tacos. So like this over here, it's kind of funny. Sometimes I've had like vulgar things come up there before. Like we did an integral once, and it was like integral e x y. This is like a Cal 2 problem. So it was like, no, it was like this. Yeah, that's what it was. So what do you think it said there? Yeah. So I had a student say like, why do you have like sex written over there? I'm like, that's not my doing. That's the computer program. So anyway, all right. I don't know. Maybe I didn't do it. Who cares? Let's just do it. We have integral r cubed over square root 4 plus r squared dr. So what was your instinct on this one?
I wanted to, we have definition, a squared plus u squared under a square root.
We do have a formula for that?
We do.
What formula was that? Forms involving. So it was which one of those?
I wanted to use the one that shows the u squared.
Are they numbered? 26? Got you. Okay. Got you. Okay, so you're on the right. You were kind of on the right track there. This is a tricky problem, which is why it's number 24. Let me see if maybe this will help. What if it was this instead? Or not instead, but what if I rewrote it this way? What if I rewrote the integral that way? So what I'm doing is I'm taking the r cubed and I'm peeling off one r. I could do that, right? Make it r squared. Now, the question would be, which one of these would you call u and which one would you call du? And why did I do this, right? I mean, it's kind of like, why did I peel off that r? Well, look at this right here. If I called this one the dv, I would have to integrate it, wouldn't I? But integration on this, what's underneath the root, I could do a basic substitution and call what's underneath the root u. The derivative of that would be what? 2r, which I would have up top. I'd be off a little bit, right? And then that would mean I call this one u with integration by parts, and the derivative of that would be 2r, right? Okay. I'm just going to see if this leads me anywhere. This is what my instinct is for this problem. So I'm going to call ur squared dv is r over square root 4 plus r squared. I'm not guaranteeing that this is going to get us to the answer. I haven't worked this problem out in probably years. But okay, let's start with this one because I think this is the easiest one. This is 2r dr, right? And then over here going up with this. I think I'll do that as scratch work right below it. I'm trying to find the antiderivative of r over square root of 4 plus r squared dr. And if I do that, right, that's what it means to go from dv up to v. I need the antiderivative. So I'm doing this really. And so I'm going to do like a little basic substitution here. I'm going to let u be the 4 plus r squared. Then du would be 2r dr. Follow? Do I have 2r dr here? I have r dr, so I'll have to multiply both sides here by 1/2. And now I can rewrite this integral. The r dr will be replaced with what? 1/2 du. So I'll pull a 1/2 out of the integral. And then I'll have this 4 plus r squared will be replaced with u. Yes? So here's what we've got. 1/2 came out. My du's in the back. Then I have 1 over the square root of u. Follow? But that's just 1/2 integral u to what power? Negative 1/2. And now I can do a power rule on that. The antiderivative of u to the negative 1/2 is 1 over 1/2 u to the 1/2, so 2, right? So yeah, the antiderivative right here will be 2u to the 1/2, right? 2u to the 1/2. But then we had a 1/2 out front. So just u to the 1/2? Okay. So this is just going to be u to the 1/2, which is the same as square root of u. Yes? But what's u? 4 plus r squared. Okay. So the antiderivative of this, right? Yeah, I'm sorry. The antiderivative of this up here, my v, is square root of 4 plus r squared. Now, does that help? Ultraviolet minus voodoo. Ultraviolet, I'm just going to write down voodoo. Look at this integral right here that I'm going to get. Yes, you'll be able to do that? That's right. If you let u be this inside, what's the derivative of that? 2r, and you've got 2r dr right there. So you're going to have everything you need for that next substitution. But I'll write it down. I think the big question still comes back to why would we do this? Like why, you know, how do you see that? And my only answer to that is because someone else showed me one time. And so now I know that that's something that I'm looking for. Was that a question?
Yeah, I mean, but it's not the only way. Like,
Perhaps there's another way. Did anyone do it a different way?
I tried to pull it off to where the r cubed came completely off, and it would be like dr over 4 the square root of 4.
Yes, but getting, okay, I'll write that down in well, I'll do it and then I'll erase it. What you're saying is you made this one right here r cubed, and you got rid of the r here, made it a 1. The problem is going from here up. You do have a formula, but that's actually what we're going to cover next class also. To get from here up, we have to make what we will call next class a trigonometric substitution. It's not a technique that we know yet, but we do have a formula for it. But the formula for it gives you what, like arc sine or something? Or formula for, no, it's not even that. It's formula 25. It's natural log of u, right? And the problem with that formula is if you use that formula, you'll have this weird, ugly natural log thing over here. And then you'll have over here 4r squared. And when you do your new integral, then you'll be stuck. You should be stuck at that point. Okay. All right, so this becomes ultraviolet minus voodoo. I'll do it in red here. So this is this integral right here, ultraviolet, so r squared square root 4 plus r squared, minus integral voodoo, which I'm going to leave the 2 in here. Why am I leaving the 2 in and not pulling it out? Because that's exactly what we will have, right? When we, this 2r dr that we get right here is exactly the derivative of what's in here. So I'm leaving the 2 in here, realizing that it'll match exactly. If I pull it out and then do my substitution, I'm going to have to come through with the 1/2 at some point. So any questions there? Now in this integral, I'm going to call this my new u, right? I'm not doing integration by parts. I'm doing basic substitution. So I'm letting my u be 4 plus r squared. My du is equal to 2r dr. I've got that exact match right there. So this becomes, what does this integral right here become? That becomes square root of, what is it? Square root of u du exactly. That's same as u to the 1/2, right? And the antiderivative of u to the 1/2 is 2/3 u to the 3/2. So this becomes 2/3 u to the 3/2. What's u? 4 plus r squared. So I'm leaving some steps out here, right? That becomes this. So I think I'm ready to write my final version of my answer down. R squared, square root, 4 plus r squared, plus or minus, right? 2/3, 4 plus r squared to the 3/2. I could write that. Would this be okay to write it this way? Square root of 4 plus r squared cubed plus c. Would that be okay? This means the same as this, doesn't it? Okay. I'm just showing it because I want you to know there's different notations for it and be comfortable with each one. You check in the back of the book. I'm not sure which version it's going to be. Did you look at the answer in the back? Or this is 24, so it was an even, yeah. I'm curious to know what it looks like in the back of the book. This is chapter 6, and this was number 24. Whoa, whoa, whoa! Come back. Yeah, definite integrals. Yeah, and I think I said that in class. They're not going to match the back. This is the problem here. Yeah, it's a definite integral, so some of it goes away. But you can see right here the way they wrote it, right? Negative 2/3 or plus r squared. So they left it as the rational exponent. All right. Interesting problem. 15. Let me look at it, and then I'll tell you if I'm mine. Oh, yeah, 15 was, I think 15 is probably one of the hardest ones out of the whole homework set. Yeah, this one right here. Yeah. The problem with this one, the issue is that there are many different choices that you could have for u and dv, and none of them look like they're going to get you anywhere good. So let me show you the correct substitution or the correct integration by parts, and then you'll just see how it all works out. The only way you really get to this is by trying a bunch of different integration by parts. So the u that I'm going to choose, or that we are going to choose, is the entire numerator. We're going to choose that x e to the 2x to be our u, and then what is left is our du. It's 1 over, right? Because it's in the denominator, so you have to put 1 over. 1 over 1 plus 2x squared. Do you all agree that we could use this as a substitution? Like it makes sense that u here is the top, and then 1 divided by this dx is our dv. Okay, now let's just see that this actually works. So let me start with doing du. Du, to take the derivative, I have to look at this as a product between these two factors, right? So I have to apply the product rule. The product rule there would give me the derivative of x, which is 1, times the e to the 2x, then plus the x times the derivative of e to the 2x. What's the derivative of e to the 2x? Itself times the derivative of what's up there, which is 2. So 2 times e to the 2x. So I put that next to the x. 2x e to the 2x dx. Agreed? Now here's, I think, the part that you really have to see. These two terms have what in common? E to the 2x. So I could factor out, just pull it out. And I'm left with what? 1 plus 2x dx. And the only reason why I think that's the critical step, seeing this, is because this is the first time that you actually see the 1 plus 2x, which is over here. You see it appear somewhere else. And that gives you some hope that you're headed in the right direction. Yes? Now, I need to get my v, so I need to go up from here. I'll do that as scratch work. I'm trying to integrate 1 over 1 plus 2x squared dx. This I can do with the basic substitution, which I would normally not show, but I'll do it real quick. If I let the entire expression in the parentheses be my u, the derivative of that is 2 dx. I have dx, but I don't have 2, so I multiply by 1/2. And then this integral becomes, the new integral is 1/2 can come out, and then 1 over u squared du. But that's just u to the negative 2? Yes? Which one, this one? Like bring the whole thing up? Yes, but it couldn't be written in here anymore. It would have to be written like this. You could write it like that. You can, but you have to make sure you account for the constant in here. That's the only tricky part. That's why I'm doing the substitution. I think once you get to a really comfortable spot with these, you would realize that you just have to really do power rule, which would give you 1 over negative 1, then all that to the negative 1. But you have to account for that constant that would have been here, so you would have had to come in here with the 1/2. But that, again, just takes time. It's kind of like, remember when I showed you all the general formula for like sine AX, integral sine AX? Said you're always going to have that 1 over A? Same thing here. This is like an AX in here, so we're always going to have a 1 over A out there when we integrate. That just depends on your comfort level. I'm showing the detail just in case you need the detail. So this right here is integral u to the negative 2 du. And that antiderivative, I have 1/2. It's 1 over negative 1 u to the negative 1, right? Power rule. And then replacing u with what u is, you get what? All that junk with the 1 plus 2x in there? Yeah. And raising something to negative 1 is the same as putting it in the denominator. So I'm going to stop here, go dot, dot, dot. I'm going to actually put the answer back up here in my table. Like, what's v? So v for us should be negative 1/2. That comes from all that negative junk here in the fraction. And then my u to the negative 1, which I'm writing as 1 over u. So it's 1 over 1 plus 2x, like that. And what's good about this? When I do my new integral, voodoo, right? V times du, this right here and this right here are going to cancel. And that's going to leave you with just the integral of e to the 2x dx, which you should be able to handle. Tricky problem. I think I've shown that to four students in my office hours and now to the whole class. So a lot of people had trouble with this one. So you want the final answer? Help me out. What should it be here? Ultraviolet. So this times this, right? So negative x e to the 2x over 2 times 1 plus 2x. That's ultraviolet, right? That's these two multiplied. Yeah? Okay, and then minus the integral voodoo. I need to go back up here. Integral, so minus the integral, but I have a negative here, right? So plus 1/2, and then this times this. The only thing left there would be e to the 2x dx. The antiderivative of e to the 2x dx is 1/2 e to the 2x. So that's going to hit that 1/2 out there and make it a 1/4 e to the 2x plus c, and then this piece down here. That should be the answer. This, and then plus that. Questions? I think that's it as far as what I'll show you today. We need to move on. All right, to start today, I wanted to remind you of some things from pre-cal that we'll be using today. So I didn't want to just start pulling them out of the bag and you're like, where'd that come from? So I just remind you of some things. I have notes to hand out to you, but I'm not going to hand them out to you until after I finish giving you these things. We have the Pythagorean identity, right? And there was another version of the Pythagorean identity. And there was a third version, right, that had cotangents and cosecants in it, but that one's not used as much, so just going to highlight those two. And then we also have what are called the power reducing formulas, where if you have something like sine squared x, you can rewrite it as 1/2 minus 1/2 cosine 2x. So if you ever have a squared sine and you don't want it to be squared anymore, you can get rid of the squared, but the whole thing turns into this. And notice that this cosine now that appears isn't squared, but the angle inside, instead of it being x like it was here, is now 2x. So you take the power down, but you wind up doubling the angle in that formula. And then there's a similar formula for cosine squared, where it's almost identical, except it's plus between them. Bless you. But both of these formulas have cosine 2x in them. The s has the subtraction and the c has the plus. I always remember it. I always remember that formula, but then subtraction, I just think s subtraction, s sine, and that's why I always remembered it. What are some other things? In your formula sheet, we have integrals. We know the antiderivative of sine x. We know the antiderivative of cosine x, right? There's actually formulas for all 6 trig functions. If you look on your formula sheet. So I do not expect for you to know to compute these. These you can look all of these up. There's another one, right? Cosecant. They're all there, right? Okay. There's also some others that we should know exist there, like secant squared x. What's the antiderivative of secant squared x? Tangent x, because the derivative of tangent x is secant squared x. What's the derivative of secant x? Secant x tangent x. That's why in your formula sheet, the integral, it has an integral for secant x tangent x. The antiderivative of secant x tangent x is secant x. And then there's other ones like the antiderivative of negative cosecant squared x. What's that? Cotangent x. Those all come from Cal 1. So just be aware that those are on your formula sheet, and if you ever get to an integral like that, you can just apply the formula. All right? Okay. I guess I'll give you the handout. Go ahead and take one, pass it down, pass them around. Here you go. All right. Now, I do not claim ownership of this handout. There's actually a guy who's been doing math online notes for a long time. His name is Paul Dawkins. And he's got a website called, I think, Paul's Online Notes or something like that. And you may or may not have ever seen it, but these are his notes. The reason I grabbed them is because I was looking for a quick summary. Do we need a few more back there? 2, 3? Just 2? 3? Okay. I was looking for a quick summary of what we're going to do today. And so if you look at this, it actually has U substitution on the very top, and then integration by parts, and then below it, it says product and some quotient of trig functions. You see that? That's what we're doing today. And then on the back, it actually has what we're going to cover next time, trig substitution, and then after that, it has partial fractions, which is what we're going to cover next Thursday. So this kind of summarizes all of it, but this is not like an official sheet that you can use on a test. It's really just because I wanted that one section right there where it says product and some quotients of trig functions. But please feel free to use it when you're at home if you want, you know, as a reference. Okay, so what we are focusing on today are trig function, or trig, what we call trig integrals. And these are integrals that involve trig functions. So the integral has a trig function in it. And just a trig function. Or just trig functions, plural. This right here is not an example of a trig integral because it has the x in front of it, right? That we would do with integration by parts. So that's not what we're referring to. We just want trig stuff in there. So your first example, which today is going to be full of examples, is trying to do the integral sine 10 up there like that, cosine x dx. So let's all make sure we're clear on what this 10 means. What does that 10 mean? There's 10 factors of sine. You could, if you wanted to, have written it like this. Now we won't, and I won't do that, but that's just for clarification. The sine function, the sine x, is being raised to the 10th power. That's what it means. So what we're going to use to solve this one is basic substitution. We go back to the very beginning. We say, okay, what do we do when we look at an integral? Do we see something in its derivative, right? Do you see something in its derivative? Yes. You see what? sine and derivative of sine is cosine. But couldn't you have also said you see cosine and derivative of cosine is negative sine? So you kind of see its derivative the other way also. So why would I not do it that way? Why would I not say here u is cosine and the derivative of it is negative sine? Because what about the 10? If this right here is the derivative, if that's our du, where's our derivative trapped? In the 10th power. And we do not want our derivative to ever be trapped in a power. We don't ever want it to turn out to be on the bottom, right? We always want it to be nice by itself. That cosine is by itself. It's in the numerator, right? If you look at this as a fraction, it's in the numerator. So the cosine x is the better candidate for our du than sine would be. So I'm going to come in here with basic substitution and let u be equal to sine x. Then the derivative of that is cosine x dx. Exactly what we have up there, isn't it? And therefore, I can rewrite this integral as u to the 10th power du. Right? There's u to the 10th. There's du exactly. Rewrite it. Now integrate. 1/11 u to the 11th plus a constant. Just applying power rule on that. And finally, what? Change u back to cosine. Was it cosine or sine? It was sine, right? Sine, so how am I going to write this? Sine x to the 11th. So I should probably go back to that other notation and put that 11 up there like that. And then plus c. Now, this problem, the reason I'm showing it to you is because as we move through problems today, if we can get it to here, we're pretty much going to say, and we could take it the rest of the way. In other words, we won't necessarily take it the rest of the way. We would just say, we know how to do that. Make sense? Okay. So our problems today, we're going to hope to get them to look like that so that we can do exactly this method. All right, here's another one. What if we have integral, and off your little cheat sheet here. The little sheet that I gave you, I said I'm going to go off today. Look at this. On the left side, you'll have it. It says, what happens if you have an integral sine nx cosine mx dx? It tells you what to do here, right? Gives you some steps. You'll see that on your sheet. The reason I'm not looking at this yet is because in the problem I just did, the power on cosine was 1. And so I'm not referring to this formula sheet yet. I only want to refer to this formula sheet when the powers on the sine and cosine are different than 1. Because if one of these is 1, then you can do exactly what I just did here. Okay, let's move on to another one now. Now I'm going to refer to this, and I'm going to write the problem underneath it. What would we do if we had sine to the 5th x cosine squared x dx? Let's first talk about why we can't just use basic substitution here. Because of the squared, right? Because if I call sine my u, the derivative of it is cosine, but my cosine is being squared, and like I said, we don't ever want our derivative, our du, to be, we just want it to be sitting there, right? Not squared or anything else. So this is not going to work that way. So let's see what they suggest we do to this. Is n odd here? Yes, n here is the power on the sine. Is that odd? Yes. So they say strip one sine out and convert the rest of to cosine. And convert rest to cosines using sine squared x equals 1 minus cosine squared x. Then use substitution to use cosine x. Okay, what the hell is all that? What they're saying is we're going to rewrite this as sine to the fourth x cosine squared x sine x dx. So what I've done here is what's being referred to as peeling off a sign or stripping a sign off. I had 5 signs, right? 5 factors of sine. So why not write it as 4 factors and just write that 5th factor out there by itself? Yes? So now don't I have something down here that like the sine x dx could be my du? But sine is the derivative of what? Cosine, right? Well, negative and all that. But I know that if I'm going to let this be my du, then I need cosines everywhere else, don't I? I have cosines here. This right here needs to be turned into cosines then. So here's what I'm going to do. I'm going to first rewrite sine to the fourth x as sine squared x squared. And then I'll have, well, I don't need parentheses, cosine squared x times sine x dx. Is that okay? Sine to the fourth is the same as taking sine squared and then squaring it again. And the reason I did that is because sine squared x, I have a formula for it, the Pythagorean Identity, that we started class with, right? This Pythagorean Identity is an equation. It's an identity. You can move things around. So to isolate sine squared, all you have to do is take the cosine squared to the other side. So sine squared x is the same as 1 minus cosine squared x. So that's what I'm doing here. So now I'm going to rewrite the integral. 1 minus cosine squared x, but then what? Squared, and then cosine squared x, and then times my sine x dx. All right. At this point, I'm ready to roll, all right? Because I have my du here, right? I know that's the derivative of cosine, and everything else has cosines there. So let's make a substitution right here. A basic substitution. No integration by parts, right? Basic substitution. U is equal to cosine x. The derivative of u is negative sine x dx. Is that all right? Remember, we want this to be our derivative, right? We want this to be the du. That's all by itself at the end. So I let my u be cosine. Well, you could, but you're going to run into some issues because this isn't negative cosine, so you'd have to start including your negatives in here. The fact that it's squared may not matter, but I would stay away from that, just because it's easier to just at the end of it all change it and bring a negative 1 out of the whole integral. Can we rewrite the integral? Okay, this new integral becomes, I'm going to pull the negative 1 out. Everyone understand that? That's my negative right there from du out here. Then what is this right here? So 1 minus u squared, but then all of that squared times u squared times du. So my cosine squared right here became u squared. My cosine squared here became u squared. My sine x dx was du. Now we have a new integral, right? New variable, new integral. This is a polynomial. It's a polynomial, right? So what I could do is I could expand this polynomial here, which means square it, so multiply times itself, FOIL it, and then come through with the u squared. And then what I'd have is a bunch of powers of u, wouldn't I? And I can integrate those term by term using power rule, which is exactly what I'm going to do. I wouldn't advise trying to do integration by parts or something on this. Just if it's a polynomial, then we should be able to handle it. So this is negative integral. When I expand that, I get 1 minus 2u squared plus u to the fourth. Then I still have u squared out there, du. Right? That's, if you square this, you get this. And then distribute the u squared through. U squared minus 2u to the fourth plus u to the 6, right? Adding exponents. We have 3 terms. Integrate term by term. Power rule on each one. I'm going to do something before I integrate. Let's see if you like this or not. You don't have to do this step, but what did I do here? I put the negative back in because I don't want to keep track of it. So I just put it back in, just change the signs of that. So I reordered it. So I have my positive term, right? This becomes positive, the other two become negative. And now I'll do power rule on each one. That's just my personal choice. You didn't have to do that. Antiderivative of this, 2/5 u to the 5th minus 1/3 u cubed minus 1/7 u to the 7th plus a constant of integration. I am assuming that from here to here now is trivial. And then I'm not done. Substitute u back in. So our final answer would be 2/5. U is what? Cosine to the 5th x minus 1/3 cosine to the 3rd x minus 1/7 cosine to the 7th x plus c. What do you think? All right. Next. What if you had something like this? It's very similar to the problem we just did. Only difference, they're both odd, right? So what do the steps say here if they're both odd? Use either 1 or 2. Now, we didn't do number 2, so let's do number 2 on this one, okay? What does 2 say? If m is odd, which would be this one right here, right? That's our m. If that's odd, it says strip out a cosine and convert everything else to sines. So it's the opposite of what we just did. If I strip a cosine out, it's going to look like this. Sine to the 5th x, cosine what? Squared x, then cosine x dx. Now this time, what's our du going to be? Our du. It's going to be the cosine, right? Because it's all nice and by itself. That means my u needs to be what? Sine, which means I need to convert all my cosines to sines. It turns out if they're both odd, you can go either way with it. But I'm showing you this way because I haven't shown you stripping a cosine off. We all right? How can I rewrite that cosine so it has sines instead? 1 minus sine squared x, right? Cosine x dx. At this point, I can make my substitution, right? U would be sine x. Du is exactly cosine x dx. So I have a perfect match, don't I? Which means I can rewrite the integral as what? U to the 5th times 1 minus u squared times du. And that's a polynomial in u. So I can clean it up and then do integration term by term, can't I? So this becomes integral u to the 5th minus u to the 7th du. You okay integrating that? 1/6 u to the 6th minus 1/8 u to the 8th, replacing u with sine. So my final answer should be 1/6 sine to the 6th x minus 1/8 sine to the 8th x plus a constant. I worked a little faster through that one, but do you all understand? Do I have any questions at all? 8, the antiderivative of u to the 7th. All right, so far, this all right? There's no cosine there. Can I make one? How? Oh, sorry, I heard way too many things at one time there. I could take a sine squared out and make it 1 minus cosine squared, but then that would be cosine squared, wouldn't it? Like peel off something? So peel off a sine again? Like that? Now, if you do that, then I think what you're saying is that you're going to want this to be your du, right? Now, if sine is going to be your du, then u needs to be your cosine, doesn't it? Are you going to be able to convert sine to the 4th to cosine? Yep, sine squared squared, like we did just a second ago. You see that? What I'm trying to show you is that we can do this exactly the way we did that other one, but even though we don't have that cosine there. I'll show it. I'm not going to go through the whole thing, but I'll show it. It's sine squared x squared, and then we have sine x dx. But converting sine squared x over to 1 minus cosine squared x squared, and then sine x dx. Now everything's in terms of cosine, isn't it? Well, except for this part. This is all cosine stuff now. So what would be your u here? It would be just cosine x. And then du would be negative sine x. So you'd be off a little bit, right? By negative. But you just bring it over. And then, is that all right? Okay, I'm going to say dot, 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 which means you could carry that the rest of the way. You could almost say that this followed the formula, right? If the n was odd, right? It says to peel off a sine, which is what we did. How would you handle this one? What if it was integral cosine to the 11th x dx? Okay, strip one of those off. Agreed? And that means your cosine x dx is going to be your du, which means it has to come from sine, which means you need to turn your cosine to the 10th power into sines. So I could convert this over to cosine squared x to the 5th power cosine x dx. Right? Cosine squared to the 5th, you multiply, 2 times 5 is 10. But cosine squared written in terms of sine is 1 minus sine squared x. Then all that to the fifth, then cosine x dx. Now this would kind of suck, wouldn't it? I mean, think about it. This would be 1 minus u squared, right? To the fifth. And so you'd have to expand that out, wouldn't you? Could you? Yeah. I mean, it's not fun, but you could do it. I'm going to say dot, dot, dot. What we're trying to get now, well, I guess as Calculus 2 students, what we want to do is we want to try and make our integrals, we want to try and get them to a point where we say, from there, we're comfortable. Like, we're okay, we could take it the rest of the way. That's what we're trying to get to. Once we're there, we won't show all that work anymore. And then there's a later point where we say, okay, here's the problem. We say, get it to an integral. Just get it to an integral. And then you get the integral like, okay, we could do that integral. You know, like it's an integral now. All right. Now something you haven't seen. I'll start with this one. Looks somewhat unassuming, right? So if you tried peeling something, right? Why wouldn't that work? Don't write this down, but why wouldn't this? Yeah, this Pythagorean does not apply unless that's squared, right? So we couldn't convert that over. Oh, wait, hold on. Maybe we just convert it now. So it becomes 1 minus sine squared, right? And you don't know how to integrate sine squared. Because if you knew how to integrate sine squared, then you could have just done the integral of cosine squared to begin with. So the question becomes, how do we do it when it's an even power like that? If it were odd power, we would peel one off, right? But it's even. So we're going to come in with that formula I gave you at the beginning of class that said, hey, look, if you ever have a cosine squared or sine squared and you want to kill the power so it's not squared anymore, you can use this formula, but what you give up is that you have to double the angle when you do it, right? Don't forget that. Whatever the angle is here, you're going to bring that power down, use the formula, double that angle. So let's go and take a look where we are here. Application of the formula. Now, some books call it the power reducing formula. Some books call it the half angle formula. All right. I always like power reducing. It just makes more sense to me that way. You're reducing the power, right? So this is going to become integral, but now it becomes two terms. It becomes 1/2 plus 1/2 cosine 2x dx, doesn't it? And that 1/2 is in both terms, so I could factor a 1/2 out, and I could have just done this. Do you all agree I could do that? In fact, if I go back to the formula right here, if you want to, you can just write, instead of this, you could have just written 1/2 times 1 minus cosine 2x. And then this formula, write 1/2 1 plus cosine 2x. This is the way I use the formulas. I use them like this because I always want to get those fractions out of there. They're just rarely given to you on a formula sheet. They're rarely given to you with the 1/2 factored out. Okay, can you integrate this? It's addition, right? Two terms. Can you integrate these term by term? Antiderivative of 1 is x. And now we're doing antiderivative of cosine ax. 1 over a sine ax. And then we have our 1/2 out front. So this should become 1/2. I'm going to put a bracket around this, do each one. Antiderivative of 1 was x. plus, we said 1/2 sine 2x plus c. So 1/2 x plus what? 1/4 sine 2x plus c. There it is. How would you convince yourself that this is correct? I mean, you'd have to take the derivative, wouldn't you? And it needs to be cosine squared x? I'm going to check it just to see. What's the derivative of 1/2 x? 1/2 plus, here's a 1/4. What's the derivative of sine of 2x? 2 cosine 2x, right? And that's just 1/2 plus 1/2 cosine 2x, which is exactly the formula for cosine squared x. So it works. I'll leave it. All right, this next one's kind of tough. I mean, not tough, but you're going to see that this can get ugly fast, all right? Sleepyhead over there. Can you nudge him? Yeah, I'm sorry to wake you, but this is an important one. All right, get up, stretch out, go out, walk in the hallway for a minute or something. Whatever you need to do. All right, I'm doing it to you. I'm punishing you here. This would be considered torture. All right, what I'm about to show you. You'll see why. Let's just do something real quick. Not with that. I'm going to go to Wolfram Alpha real quick and see what the answer is, all right? Because I want you to see where we're headed with this. I want to integrate what was it? Cosine of x, right? But then raised to the 6. Whoa. Maybe that's not so bad. What do you think? Oh, well, no, because that's not the form we're going to get. Well, which form are we going to get? No, we're not going to get that one. We'll probably get this one right here. Yeah, that's not so bad, maybe. We'll wait till you see what it's going to take to get there. Okay, we have what? Cosine even power, right? Even power? Well, the only way we can do even power is if we can't peel anything off, right? We already said that if we try peeling, we won't have anything to convert over. So, well, I don't know. Did we say that? What would happen if I just try and peel a cosine off? What would happen? What's wrong with this? What can't we do? We have a 5, right? 5 I can't do. See, I eventually would want to get that to a cosine squared. I couldn't do a cosine squared because it's cosine to the 5th. So there's no way I could get to the 5th power from squared. Like when it was 4 there, I could go squared, squared, right? Like if that was cosine the 4th, I'd go, that's cosine squared, squared. Understand? So because it's 5, I cannot do that. But what I can do is reduce the power. So I can do this if you agree. I can write that as cosine squared x to the what? 3rd, right? I did not peel anything off. But what's cosine squared x when you power reduce it? It's 1/2 times 1 plus cosine 2x, right? But then I want that to the 3rd power. Now notice I used my version of the formula, not my version, but the version where it's the 1/2 has been pulled out. I'm doing that because I'm going to cube this, right? That's what I'm going to do right now. And I can cube 1/2. What's 1/2 cubed? 1/8, right? And I can just push that out of the integral right now. So I'm going to rewrite this as 1/8 integral. And what I still had there was 1 plus cosine 2x cubed dx. Everyone still on board? Now you have to cube that expression. You have to cube it. Maybe I should bring up a new page and then come back to this. What's 1 plus cosine 2x times 1 plus cosine 2x times 1 plus cosine 2x? One plus 3 cosine squared 2x plus 3 cosine 2x. Hold on, this one's not squared. This one's squared. This one cosine cubed 2x. That's what you would get if you multiply all those together. Anyone know how I'm doing that? The Pascal's triangle, if you've seen that, that's all I'm doing there. If you don't know what I'm talking about, don't worry about it. If not, you'd have to do it by hand, okay? So you have to go here times here, here times here, here times here, here times here. Then once you do that and figure out what all that is, then you come in, you multiply this one, distribute these through to that, and you should get this. Okay? Questions? No? Now we're going to integrate all that. So we should have back here 1/8 integral. It was 1 plus 3 cosine 2x plus 3 cosine squared 2x plus cosine cubed 2x, wasn't it? dx, I mean, if you believe what I said, right? By the way, if you go to Wolfram Alpha and you want to multiply something out like that, I think you can just type it in. But if you write expand, that's the operation that Wolfram Alpha will understand is cubed, right? So if I type in expand 1 plus cosine 2x cubed, whoa, yeah, Wolfram Alpha is too wow. Why didn't it expand that properly? Man, because what it's trying to do here is it's using all these double angle identities. Let me change that to just x, and it'll keep it cleaner, I'm pretty sure. Yeah. So it's your last, so it's the 1, and then it's a 3 in front of the cosine, and then it's a 3 in front of the cosine squared, and then it's the cosine cubed. So if you just put 2x, 2x, 2x in there, that matches. See, sometimes Wolfram Alpha is too smart for its own good, right? It just starts trying to simplify everything. All right. Okay. Do you see what sucks about this? What's the antiderivative of 1? X. That won't be a problem. Antiderivative of 3 cosine AX would be, yeah, 1/2 sine 2x, but then you have a 3 in front. So you got to do that. Those two look okay, right? How about this one? So power reduce on that. So because this one's squared again, we know we can't handle squares. We're going to have to power reduce just that one. And then what about this one, cosine cubed? We can peel a cosine off because it's an odd power on cosine, and then do what we did before. You see all this? I mean, it's a mess. But that's life. Sometimes that's just the way it goes. So how about this? 1/8 x. I'm doing, in red is me already integrating, okay? The antiderivative of 1 is x, but then I put the 1/8 in front of it, okay? The antiderivative of cosine 2x, we said was 1/2 sine 2x, right? Times 3, so 3/2 sine 2x, times 1/8, so 3/16. So plus 3/16 sine 2x. Now let me go back to the stuff I'm going to have to integrate. Plus 3/8 integral cosine squared 2x dx plus 1/8 integral cosine cubed 2x dx. Y'all see what I did? These two become these. This one, I put the 3 in front or on top of the 8, and I'm doing cosine squared 2x. This one right here by itself, and then the 1/8 came along. No questions? No, can't box that. Can't box that. So we have two integrals that we need to figure out, right? This one and this one. So I'm going to go to a new page and do each one. I'll come back to this page. This is kind of where my scratch work was. I'm doing integral cosine squared what? 2x. Don't forget that it's 2x. It's not x. When I do this integral, I use my formula. It becomes integral 1/2 1 plus what? Cosine 4x. 4x, yes. Because the angle doubles, right? That's the give and the take. The power comes down, the angle doubles. So if you already had 2 in there, it's got to become 4. The 1/2 can come out. Do I have any questions? Can you do the antiderivative of each of those? Okay, they are, so we get half. I'll leave the half for now. X and then antiderivative cosine 4x, 1/4 sine 4x. Then plus a constant, right? And we'll just throw that constant in later, but I'll put it in now for this particular problem. Then we distribute our 1/2 through, right? Oh yeah, 3/8. This is just that part that I boxed from the previous page, right? Not 1/4, 1/8 sine 4x. That's it right there. Yeah, yeah. That, and remember, that's just going to replace this, right? We've still got the 3/8 in front. If you wanted to, you could have done the problem over here with the 3/8 in front. That would be okay. It's your personal call there. Just remember where it is. Don't forget about it. The other integral I need to do, which I'll have to do a new page for, I still have to do integral cosine cubed 2x, right? Which we said we would use the peeling off part, the peeling off thing. But just make sure you remember that you're using 2x in there, not x, right? Peel one off. Rewrite the cosine squared 2x as what? 1 minus sine squared 2x. Then cosine 2x dx. Why did I do that? So I can make what substitution here? U is, yeah, the du is the cosine 2x dx, so my u is sine 2x. My du, because the chain rule is 2 cosine 2x dx. So my u is the sine 2x in here. The derivative of that is cosine 2x, but then the derivative of the 2x is 2. So make sure you account for that 2 right there. Chain rule. And that does not match what I have, does it? So I have to scale everything by 1/2, which means 1/2 is going to pop out of this integral. Can you appreciate how quickly this is accelerating, right? Do you see why we don't have time for like power rule anymore? Like there's just no time to talk about power rule during a class. Like, all right, so what does my new integral become? This new integral is 1/2. I'll pull that 1/2 out. Integral 1 minus u squared du. Can you tell me what the antiderivative of this is? U minus 1/3 u cubed. But what's still in front of that? 1/2. Distribute the 1/2 through. We have 1/2 u minus 1/6 u cubed, plus a constant, but I'm not even caring about the constant anymore. And then what's the u here? Sine 2x, right? So 1/2 sine 2x minus 1/6 sine cubed 2x, or you could say sine 2x cubed. And that's it, right? How do y'all feel? I mean, do you feel like, yes, we're, it's okay, or is it more of like an airplane with like things starting to come off the sides and, rivets are starting to peel? I mean, how do you feel? Definitely going to have to practice, right? Can we go back to the answer now? Let's go try and put this answer together, which was back here. Let's try and keep track of all of our constants. We have a 1/8 x plus a 3/16 sine 2x plus, now that 3/8 distributes through to this one, right? So 3/8 times this is 3/16 x, and 3/8 times this is 3/64, right? Help me out. Okay, what was the first one? I already forgot. 3/16 x plus 3/64 sine 4x, and then we have this plus the 1/8 distributes to these. So we'll have 1/16 and it was 1/8, so 1/48. Yes? And there's a minus. So we get plus 1/16. Well, 1/16 what? Sine just 2x. Sine cubed 2x. Plus a constant of integration. There's more. There's more. There's some like terms here. We have 1/8 x plus 3/16 x, which is 5/16 x. And then we have some like terms here. We have a 3/16 2x and a 1/16 2x that we're adding together. That's 4/16, which is the same as 1/4. So we have 1/4 2x, sine 2x, sorry. And then everything else, right? The rest are not like terms. Here we go. Yeah, it's definitely considered torture right there. And it's even more torture if you make this like cosine to the 8th. Because imagine that, you've got to go cosine squared this time to the 4th, which means when you expand it, you get even bigger thing here, and then each one of those goes a different way. And it actually turns out that if you do that, one of these will be a cosine to the 4th, which then you'll have to do everything we just did as one of those integrals. So it might be nice if we had like a reduction formula for cosine, wouldn't it? And if you look in the back, I don't know if your formula sheet, no, we said it doesn't, but there is a, let me see if there's a reduction for cosine to the n. Yes, there is a reduction formula for cosine to the n. It's formula 74. You see, but I mean, it's a reduction formula. So all it does is it creates a new integral, which then you'd have to do reduction formula again, but you can avoid all of this with it. I'm just letting you know it exists, all right? So someone said, look, this could really suck. Maybe I can come up with a formula for it, and that's what happened. Someone came up with a formula for it. You don't have to know it. Just know it. If you're like in an engineering analysis course and you get, you get to something like this, you wouldn't want to do all this. You'd probably just want to go to your reduction formula instead. All right. Now, if that doesn't get you excited, I don't know if I'm going to be able to get you excited at all this semester. All right. Have we looked at, what if they're both even? What if sine and cosine are both even? I can't believe it's already 12:20. Ridiculous. What if they're both even? Well, same story. We can't do much. We have to just use our formulas to reduce the powers. So I would rewrite this as, first of all, that sine squared is 1/2 1 minus cosine 2x. Right? That's what this is. Do you agree? And then this one is the 1/2 1 plus cosine 2x, but then squared dx. So I'd have to do the power, the power reducing on this. I'm writing this as cosine squared x squared. Then what? How about we pull the 1/2 out? And when I square this 1/2, it's a 1/4. So pull that everything out as a 1/8. And then I still had 1 minus cosine 2x, and then over here I had what? 1 plus cosine 2x squared. Now I wrote it instead of squared, I wrote them side by side. Anybody have an idea why I did that? These are difference of squares, aren't they, the first two? And it might be a little easier for me to do that before I multiply it all through. Difference of squares with these two, when you do this, the middle terms go away, right? So all you get are the outer terms. So 1 times 1, and then you get minus what? Cosine squared 2x. And then we multiply that with 1 plus, bless you, cosine 2x dx. And now we do again like a foiling. And when we do that, we should be ready to approach this integral. So 1 times 1 is 1. And I have a cosine 2x plus a cosine squared 2x, and then a minus cosine cubed 2x dx. Do you all at least understand the multiplication I did here to get all this? Antiderivative of 1, x, no problem. Antiderivative cosine 2x, 1/2 sine 2x. This one, power reduce again, right? So that's going to turn into that 1/2 1 plus cosine 4x. This one, so peel one cosine off and then go from there. That's a lot of work. I'm not doing it. But you see how it would work, right? So if you follow the thing on here, it says if m and n are both even, use double angle or half angle formulas to reduce the. So when they say double angle, half angle on this, they mean that thing I just showed you, the 1/2. You know, I'm gonna have to think about it. Let me think about it. What I would like for you to do is go home and work off of this, use it, but try and put as much of it to memory as you can. Also, that's one of the big debates we're having in our math department right now. Is how much do we give our students on a test? And there's kind of different ideas on that. My feeling is that in the real world, you're never really stuck in a room with nothing. You always have some reference, some resource. So I don't like the idea of just like locking you down saying, okay, you get this one sheet of paper, like good luck. But at the same time, we have to be comparable, like class to class. A student who gets an A in this class should be comparable to someone who gets an A in another class. And if one student gets to use all the formulas and the other one doesn't, then is that really giving you a good indication that they're at the same place? So we haven't resolved that. So what I'll probably do is talk with a few of the colleagues that I want to be on the same page with, and then we'll agree. And I would anticipate that most likely you'd have something. My way I've done it in the past is I let you have those formula sheets, right? And I usually let you have one sheet of additional formulas or steps or things that you want to write down. You just can't work problems out. That's the way I've always done it in the past. And that way, you kind of create the things that you need, that you're going to need, which means you have to take the time to do that, which hopefully helps you prepare. And I have no restriction on calculators. However, I know what they're capable of, so you still have to show your work. So you couldn't, like on a test, have this integral and then all of a sudden have the answer there and there's no work. It's just like, okay. But you can check it. I have no problem with you checking it. But if you have a TI-89, be careful because it's almost kind of like Wolfram Alpha. It's a little smarter than we know it is. And so look at this answer. What was the answer that we had? It was integrate. I don't know if our answers match. Integrate, what was it? Cosine. It was cosine x to the 6th. We finished that one, right? We got the full answer on that one? Okay, let's see if it matches here. Did we have 5/16 x? Did we have 5/64 sine 2x? Did we have a sine 2x term? Did we have a sine 4x term? Did it have a 9 in front of it? No. Did we have a sine 6x term? No. They did something more than what we did. We got to this point right here. They took this and used additional formulas to make this a sine 6x somehow. And when they did that, it actually added some sine 2x's and sine 4x's over here. So if you're taking a test and you put the answer that the TI-89 is saying, but you have no way of getting to it, I see it, then I know that you're basically using the computer, but you have no idea how to get to the answer. So what I'm looking for is all this stuff. I'm looking for the work. Does that answer your question? Yeah. Okay. 15 minutes. We haven't even talked about integrals that have the other trig functions like tangent and secant. So what if we have something like this? Integral tangent to the 6th x secant to the 4th x dx. According to your sheet here, what do you do if you have an odd power in n? Well, we don't have an odd power in n. What do we have here? Even power. Well, it doesn't even talk about that. What about this power over here? That's our m. According to the formula, that's m and this n. What if m is even? What does it say to do? Strip 2 secants out. So if I strip 2 secants out, I have tangent to the 6th x. I write secant squared x times secant squared x dx. Now, what's the reasoning in this? Secant squared x dx is the derivative of what? Tangent, right? This is the derivative of tangent. So by peeling the secant squared off, I can figure out what the answer is if I can convert all this over to tangents. See how this is similar to what we did before? And secant squared, I can convert using the Pythagorean identity, that secant squared is 1 plus tangent squared. So now I'm going to rewrite this as tangent to the 6th x times 1 plus tangent squared x, then your secant squared x dx. Yeah? Everything's tangents except that piece over there, which is our du. I'm ready for a substitution. U is tangent x. Du is secant squared x dx. That's the derivative of tangent. Rewrite the integral in terms of u. What do you have? U to the 6th, parentheses, 1 plus u squared, and then secant squared dx, secant squared x dx is du. And from there, dot, 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 right? You would get 1/7 tangent to the 7th x plus 1/9 tangent to the 9th x plus c. So it's pretty similar to what we did before, right? Trying to peel something off to get things to work out so we make a basic substitution. 12 minutes, 12 minutes, 12 minutes. And we proceed. Integral tangent to the 5th x secant to the 7th x dx. Remember, the n is the one on tangent, the m is the one on secant. So according to this sheet here, my n is odd, isn't it? And if n is odd, then I'm going to go ahead and peel off a tangent this time. And what? Peel off a secant. I'm going to peel a secant and a tangent off. I wonder why I would do that. Because if I put over here, I said I'm peeling a secant and a tangent, I'll write it in that order. Secant x and a tangent x. This right here, secant x tangent x, is the derivative of secant x. So if I can write all of this in terms of secant, then I have its derivative right there. So I'm going to convert this time the tangent over to secant. Now, unfortunately, it's tangent to the 4th, which means I'm going to have to write it as tangent squared squared then secant to the 6th. And what's tangent squared x by the Pythagorean identity? Secant squared x minus 1. So secant squared x minus 1, but then squared, and then secant to the 6th x, and then secant x tangent x dx. So remember where we're breaking this off, right? This is where we're going to break it off. That's our du right there, isn't it? What's u? Secant x. What's du? Secant x tangent x dx. Rewriting the integral then, u squared minus 1 squared u to the 6th du. Let's see. Let me see if we can do this in our heads. We get u to the 4th and then times u to the 6th, u to the 10th. So 1/11th secant to the 11th x. Then we'll have a minus 2u squared u to the 8th. So minus 1/9 secant to the 9th x. And then the last one was plus 1. So plus 1/7 secant to the 7th x plus c. I'm not showing the work, right? But it's a polynomial now. So expand it, multiply through, power rule on each one, replace u with secant. We're done. I have 8 minutes, which means I still have time. What would you do with this one? If it was just tangent cubed x dx. What do you think you would do? Okay, if you strip a tangent out, then what? Oh, sorry. What though? I mean, is this going to work? Look at, because the derivative, if we're saying this is du, then tangent is the derivative of what? No. Right? Just hang in there. Do you agree with this? Distributing the tangent x dx through, we get this. Now, isn't secant squared x the derivative of tangent? The secant squared x is the derivative of tangent. No. Derivative of tangent is secant squared. That's what. So the derivative of this is that. So I see something in its derivative. So that one's okay. What about this one? Remember I said in the formula sheet, we haven't, if formulas, we don't have to prove them, the formulas for all the integrals of just the trig function by itself. So you go to your formula. This one I'm just going to do mentally. This is going to be 1/2 tan squared x. That's this one, antiderivative. And then over here in your formula sheet, it is, I don't have that memorized. Yeah, natural log secant absolute value of secant x plus a constant. So that one worked also. All right. I can't go any further. I still didn't do one or two examples I wanted to do. Well, I think that 1 through 27 or 1 through 28, page 326, 1 through 28. Oh, but like I've said, always start with the odds. If you work at least the odds, you're at least, getting that much, right? And then if you can have time, do all the evens also. Remember, don't treat these as indefinite integrals, so if they have little numbers on them, you're going to have to just ignore it. See how it goes, all right? That's a lot of work right there. We'll come back next week. We'll finish up this section. Then we'll have one more section, and then that'll be it for techniques of integration. We'll be done with techniques. So there's like two more major topics with integration, two more major topics. Attendance, let me call some names here. Let's see, 1, 2, 5. I'm going to guess, let me see if I can guess who's not here. Is Loan here? Loan, last name Nguyen? Last name Nguyen. Okay, that means everyone else is here, so y'all can go. Yes.